Hi, I'm Aldrin Lindogan, and I'm here to present my Arcdes thesis proposal entitled Hybrid Biotechnology Garden, a research conservation facility for endemic plant functional biodiversity through meteorological architecture. So let's get into it, and let's get into the first part. Part 1 is introduction. This is the map of world's biodiversity hotspot, and Philippines is one of them. Philippines is considered a mega biodiversity hotspot comprising 70% of the world's flora and fauna. It is also two-thirds of the world's biodiversity. This is the endemic percentage of plant families in the country, which is 40 to 60%, meaning 40 to 60% of plants that we can see here are unique to that geographical region or unique to the country. So what is the problem with the current endemic plant biodiversity? Based on the Kew Gardens rates of modern extinction in endemic plants, it states that there are 59 species that went extinct in just 100 years. There's also a 111 years decrease in seed plant life expectancy and a 221% increase in seed plant extinction rate. Why? These are the top three biodiversity killers. So first we have overexploitation, and then agricultural activity, and then the third one is urban development. So this is the map of world plant extinction rate. It shows the extinction rate of the different countries in terms of their species. And this is the world plant reemergence map. So these are the species that reemerge from extinction in those 100 years. So in terms of the country, we have 41 to 79 species that went extinct in 100 years, and only 1 to 2 species reemerge from those extinction. So this shows the effectivity of the conservation strategy that the government is doing in order to mitigate the rapid plant extinction in the country and in the world. So what is being done to solve this kind of problem? Based on the global strategy for plant conservation, which targets from the years 2011 to 2020, objective number two, plant diversity is urgently and effectively conserved. It states that 75% of threatened plant species should be extracted to ex situ collections, while 20% of the genetic resource should be available for recovery and restoration programs. So, what is a plant genetic resource collection? A plant genetic resource collection is a germplasm. A germplasm is a collective germ cells or genetic resource of a whole culture. The facilities that stores this kind of germplasm are called germplasm facilities. So there are two types of germplasms. The first one is in situ. In situ germplasm is the process of protecting an endangered plant or animal species by using legislation to protect a specific geographical region in the country. An example of this is Region 8 Samar National Park and Region 2 Batanes Group of Islands. The second type is XC2 germplasm. This is the process of protecting an endangered species by extracting it outside its natural habitat and creating conducive artificial environments. An example of this is the University of the Philippines, Los Baños, and the Eden Project in the United Kingdom. So what is the status of Philippine genetic resource collection? This is the status of ex situ collections in the country. So we have three rattan gene banks, two palmetto gene banks, two mangrovetum gene banks, one gene bank for agroforestry, three bambusetum, and 10 public botanical gardens in the country. In terms of the in situ collections, Malyari stated that there are three parameters in terms of measuring the effectivity of in situ collections. So the first one is coverage. So it tells us that only 11% out of the 27% Philippine biodiversity hotspot is protected. And then the second parameter is management effectiveness. It tells us that only 40% out of the 85% legal protected area have a detailed management plan. And the third parameter is overlap of biodiversity. There's a 64% mismatch between the protected areas and the key biodiversity areas in the Philippines. So now we're going to the part two, or the research of the study. This is the statement of the problem. One of the main root causes of the rapid plant extinction in the Philippines is due to inadequate biodiversity coverage of facilities and fragmented strategy for biodiversity conservation. The research goal for that is to propose a modern genetic conservation facility that will be a common venue for hybrid conservation strategies and an improvement on plant biodiversity genetic coverage. So here we have the research questions on the left and the research objectives on the right. The first research question is how to provide an effective typology for better genetic coverage integrated with hybrid plant conservation strategy. The research objective for that is to provide an effective plant coverage and germplasm conservation typology by combining in-site and off-site conservation strategy. The second research question is what type of spaces do scientists need to study plant growth? The research objective for that is to determine types of spaces and systems used for studying efficient plant growth experimentation by looking at case studies of modern systems on germplasm utilization. The third research question is what systems and protocols do scientists execute to do plant growth and conservation studies? The research objective for that is to determine protocols on plant growth and conservation studies by looking at the process of germplasm systems and systems on biotechnology. The fourth research question is how to provide a collaborative social and scientific space that will improve cooperation and information sharing between scientists and the public. The research objective for that is to provide a collaborative, social, and scientific space that will improve cooperation and information sharing through ecomimesis design. So the first case study is the Royal Botanic Gardens in Kew. Located in southwest London, Kew is the largest man-made biodiversity in the world. A 132-hectare of land intended for plant conservation, research and development of public awareness towards plant physiology, population, taxa, and protection of endangered plant species. The second case study is the Eden Project, which is an environmental facility focusing on the interrelation of plants and humans in terms of their effect on the ecosystem and the natural systems of the planet. The third case study is Eco Boulevard in Vallecas. So the architecture created a social nature activity, bioclimatic adaptation. So how does this happen in the architecture? So this is the programming of the architecture. You can notice that humans are programmed below the plants so that the humans can produce the carbon dioxide that the plants need to produce oxygen. And then on the other hand, the plants would now produce oxygen for the humans. So these are the natural systems of the natural components in the architecture. And the theory that is used in that architecture is psychomimesis design, which focuses on the programming of homeostatic functional diversity with its components the homeostasis, biodiversity, spatial efficiency, ecological cybernetics, succession, and the biogeochemical cycles, or basically the programming of the living components of the architecture. The fourth case study is J-Deco Park. The design focuses on the interrelation of humidity levels, human activity in the architectural space. So here we can see the simulation of the southwest winds in the site, and you can see that it creates cold spots around the site. The architect placed the architecture intervention in those sites, and on the right side, based on the north wind speed simulation, you can see the effect of the architecture creating humidity levels on those zones. So the theory that is used in this process is the meteorological architecture, or programming of the microclimate. The components are heat and light source, insulation, color reflectance, ventilation, relative humidity, and airflow. It is the programming of the non-living things in the architecture. Part three are the frameworks. So here is the conservation strategy that we're going to use. The conservation-oriented restoration. Conservation-oriented restoration by Sergey Wallis proposes that we combine a hybrid typology by combining the in situ and the ex situ germplasm, creating this facility we call an interquasi germplasm. An interquasi germplasm will be built on a protected buffer zone of a protected site mandated by the government. And there, the hybrid facility would extract 70% of the genetic resource from the plants, and then 20% of the genetic resource would be propagated into different suitable protected zones. And some of it would be reintroduced to the protected site. So the systems that is working on that hybrid typology is first the plant acquisition, which focuses on the quarantine and culture control of the plants. And then the second phase is the plant conservation and management, which focuses on the horizontal and vertical propagation of the plants. And then the germplasm utilization is the last, or how are we going to utilize the information that we get through provision of libraries or records keeping areas that can be used for data collection and data gathering in order to learn more about plant biodiversity in the country. And then now we inject the architectural theories on that phases of conservation. We have meteorological architecture and ecomimesis design. And then there we see a median type of theory. So what is that theory? So in terms of the theoretical framework, now we combine the two architectural theories, creating the experimental biomes. The experimental biomes would be the median, and then the experimental biomes would be divided into three types of spaces: the natural, semi natural, and artificial spaces. And then we combine now the conservation strategy with the theoretical framework, creating my thesis and the thesis proposal, which we call the biotechnology gardens. The biotechnology gardens comprising of three components: the plant growth simulation, experimental biomes, which is the theoretical framework, and the biome atmospheric morphogenesis. These are now the basic components that we will use for designing the facilities. And this is the analytical framework on how I came up with the analysis of the different problems and data that I had in the RRLs. And this is the synthesis of those RRLs into creating the proposed hybrid biotechnology garden for rapid plant extinction mitigation. Now for part 4, part T, site selection. Site criteria. The site should be a priority for conservation in the Philippines. The site should have an existing protected area. The site should have an existing buffer zone and should have a big zoning area. It should have a minimum of 1 hectares for the facility to have indoor and outdoor growing area. And then these are now the top 5 biggest regional protected areas in the Philippines. And you can see that Region 2 is the biggest one, but it doesn't have an existing buffer zone mandated by the government. So we go to Region 8. This is the map of Region 8, and Region 8 is Eastern Samar. So these are the list of protected areas in Region 8, and we rank them to the top 3 biggest protected areas. And we can see that Samar Natural Park is the biggest one, and it also has an existing buffer zone mandated by the government. It is also considered the center for plant diversity. And this is the map of Region 8 Samar Natural Park. The green one is Samar Natural Park itself. And then the yellow one that is surrounding it is the buffer zone mandated by the government. So in terms of site selection, we still try to choose the biggest cities or municipalities within the area of the buffer zone or the yellow zone in the map to have a connection in terms of the logistic concerns of plants. So the biggest city around the periphery of the protected site is Calbayog. So that is the part of Calbayog City with the protected site. And now we go to the macro site analysis. So this is Calbayog City, Region 8, west of Samar Island, which comprises 90,300 hectares of land. And this is a protected site. This is the mandated buffer zone. These are the road networks. So you have Calbayog-Catarman Road, Patong Hilino Road, the Maharlika Highway. And then these are the major sources of income. So the central business district is along the coastline, and their major sources of income is ecotourism, commercial and trade, fishing, and industrial activity. And then the urban growth pattern can be observed as the linear development. So the biggest concentration of residential activity are along the road networks. Then our site location is at the periphery of the city near the protected area. So meso site analysis. This is now our site, Barangay Bagong Lipunan, northeast of Calbayog, which is 50 hectares. The residential areas in the site is Barangay Patong, Barangay Bagong Lipunan itself, and Osmeña Samar. And then the existing road network is the Patong Hilino Road, which is connected to the city central district, 13.5 kilometers from the Calbayog city central district. So this is the type 2 climate of the site. It has pronounced rainfall from November to April, a wet season from May to October, and an average rain of 2,708 millimeter per year, an average temperature of 26.8 degrees Celsius. And this is the sun path, which is southeast to southwest. This is the contour map. So you can see also that it is a land valley formation. So the blue ones are the 45 meters above sea level area, and it goes up on the sides from 186 meters to 204 meters above sea level. The yellow to orange colors. This is a slope map by DNR. DNR recommends that it is buildable and build only with continuous monitoring. And then the flood hazard map, this is the 100-year projection. And then the grassland versus forested area. The grassland are the recommended buildable zones since we don't have to rezone some trees to different parts of the site. And then this is the overlap of grassland versus the flood hazard map to see which grasslands are not in the floodplain. And then the buffer zone of Summer Natural Park, which is mandated where we will build the facility for the growth of the plants. And then this is the SWOT analysis of the site. So the strengths are that we have the site in road proximity, we have an abundance of endemic and native plant species, and then the area is allotted for ecotourism. The weaknesses is that we have a sloping terrain. The opportunities is that we can build a germplasm, a sanctuary, and an ecotourism industry facility. The threats is that we have flood and heavy precipitation. And then the first proposed site for microsites is the germplasm acquisition. The criteria for choosing the site is that the acquisition zone should be near the main road for efficient transfer of plants from different cities around the country, connected to Calbayog and then to other major cities of the Philippines. So the second part is the growth biomes itself. The growth biomes should be inside the mandated buffer zone. This is to facilitate efficient transfer from the natural zones into the artificial zones where the scientists would study the different plants in their laboratories. And then these are now the sight lines for those two microsites. And these are the two microsites with their areas. So the germplasm acquisition is 1.7 hectare, and then the growth biome is 8 hectares. Microsite 1 analysis. So the plant acquisition and quarantine phase is 1.7 hectares. The residential area is adjacent to the site, which is Barangay Bagong Lipunan. And then we have a existing road network, which is the Patong Hilino Road. And then we have the flood hazard map here, the red one. So the SWOT analysis for site 1 is that the strengths is we have a road proximity, we are near the community, the area is allotted for ecotourism, and then the weaknesses is that the noise from the residential area. The opportunities is we can create a community-based garden, and we can create a logistics area for plant transfer and quarantine. The threats would be one-third of the site is a floodplain, and then heavy precipitation. Microsite 2 analysis. So this is the experimental growth biomes. So the site would be inside the Summer Natural Park buffer zone, which is used through the conservation strategy that we have. This is the grassland versus forested area in the site. And this is the flood hazard zone. So it's not in the flood basin since it's above. It has a high sloping area. And then this is the slope map by DNR. And then the strength is that it is in the forest zone, so it would facilitate efficient transfer of specimen of germplasm in the protected site buffer zone, so it is used through the conservation strategy that we use. The weaknesses is that we have a sloping terrain and there are no existing road networks. The opportunities is we can build an arboretum and an observatory garden. The threats is that we can have heavy precipitation. The program. So the macro site planning, we will start with the macro division of spaces. This is the proposed road network. And this is the programmatic framework of spaces. So we have biotechnology gardens, the proposed typology of the project. And then we have the three germplasm system phases, the plant acquisition, plant growth, and germplasm utilization. And then we have the below it are the users with the orange boxes. And then the yellow boxes are the major garden spaces. The white boxes are the spaces in those users, no, and gardens. So the projected capacity and user demographics, the type of users is that we have researchers and students, horticulturists and research extension staff, administrative staff, plants, and allowed visitors per day. The projection is based on existing typologies with germplasm uses. And these are the standard dimension of space for germplasm facilities. And these are now the first type of spaces that we have in our theoretical framework, the natural zones. So natural zones are space used for planting on outdoor without architecture or a landscape intervention. These spaces will be taken care of horticulturists. These are the natural zone, which are just the grasslands of the site. And then we have the proposed arboretum zone where we will plant the endemic trees that we get from the different parts of Mindanao and Visayas area. The arboretum capacity is 20,000 trees. And then we have the proposed flowering garden zones, which has a capacity of 10,000 flowering plants, which would be the house of different flowering plants from around Visayas and Mindanao area. And these are now the second type of spaces, the semi-natural spaces. Our architecture program with the consideration of soil, water, light, and gravity, which are the basic tropisms of plant growth physiology. So we can see here in the programmatic spaces are the spaces in the semi-natural zones. And then the last type are the artificial zones. So artificial spaces are architecture program for human use. These are public, administrative, and laboratory spaces. So the programmatic spaces that is included in those type of zones are on the right side. And now for site 1, plant acquisition. The design process for the site 1 is that we have the site, and then we just excluded the one with the buildable part because the other side, the one third, would be flood prone areas. And then we created a simple circulation for the service road. And then we now have the division of spaces based on the theoretical framework. And then the development of ecological corridor based on the ecomimesis design. And then the provision of acquisition spaces for plant germplasm. These are the site considerations. You have Patong Helino Road, the proposed road to growth biome, and then the topography. The site is relatively flat, and then it is also adjacent to Barangay Bagong Lipunan. And some planning considerations is that we can build a medicinal and edible garden as an intermediate boundary between Bagong Lipunan and the plant acquisition. And then on the other side is the rain garden as a buffer zone for the flood-prone area of the site. So this is now the bubble diagram with its division based on the theoretical framework. So you can see that the semi-natural space acts as a buffer zone for the flood, and then the public hub for the residents of Barangay Bagong Lipunan to integrate plant conservation in their daily lives. And these are the division of space based on the germplasm system phases. And these are the percentage of the spaces based on their use versus the site. And the floor plan zonings. These are the different floor plan zonings. And this is now the floor plan. So this is the isometric diagram showing the floor plan. So the first type of space is the edible garden, the medicinal garden, the lounge, the cafeteria, the comfort rooms, utility access, mechanical rooms, then plant introduction office and labeling, meeting room, waiting areas, dark room, seed packaging room, seed drying room, seed testing laboratories, herbarium lounge, the records keeping room, the multipurpose hall, the herbarium storage, then the back of the house, the library, the plant quarantine laboratory, the seed storage, the dormitory lounge, the security room, the dormitory itself, the rain garden, and then the parking. So this is the structural of the site. The columns are the cyan colored blocks, and then this is the vehicular circulation, the service road. And this is the configuration of seed testing laboratories, no, with a capacity of 17 people and an area of 217 meters square. This is the specific space computation. And these are the required spaces for the seed testing laboratories. And these are the different space computation of the herbarium and the dormitory. So this is now the site development plan. Starting from the left, the edible garden, the plant acquisition itself, the herbarium on the lower left, and then the medicinal garden on top near the parking area, the rain garden, the road to growth biome, the dormitory, and then a seed storage. This is the perspective of the public gardens, where the people of Barangay Bagong Lipunan can plant their food and interact with the different scientists. And these are the plant lists based on the cross-reference of Dr. Madulid, Dr. Lantican, and the DNR list of endemic functional diverse plant species in Samar. And then site 2, experimental growth biome. This is the macro growth biome bubble diagram, which also divides it based on the theoretical framework, the semi-natural space and the artificial space. And then the artificial space are located near the proposed road to facilitate easy access to transfer plant germplasm from acquisition to growth biome. So this is the semi-natural space also and the artificial space of the light and gravitropism biome. And these are the division of space based on the germplasm system phases. And these are the percentage of every space versus the area of the site. This is the gravitropism growth biome, the first growth biome. So gravitropism is a process of differential growth by a plant in response to the direction of gravitational pull. So the scientists stimulate plants through the process of gravistimulation, which is the stimulation of plant growth by changing the orientation and angle of the soil, where the plant is growing to create a differential growth. So that shows is the experiment on the right side of the slide. So the design concept and the design concept formula is based on the conceptual framework. So we have the biotechnology gardens with its components, the biomatmospheric morphogenesis, which is the orientation and angle of the plane of the garden, the plant growth simulation, which is gravitropism, and then the experimental biome, which is the theoretical framework or the types of spaces for germplasm. So this is now the design implementation. This is the gravitropism biome bubble diagram. And this is the floor plan of the gravitropism biome. And this is now the isometric diagram of the floor plan. So the first space is the arboretum part connecting it from the road, and then the lounge, the logistic storage for plant transfer, the seed testing laboratory, the comfort rooms, the records area for growth factor data, the study classrooms, the mechanical room and generator, the gravitropism landscape, and the landscape observatories where we will observe the plant's growth. And then the load-bearing scheme that will support the, uh, the scheme itself or the architecture itself. So the configuration of the gravitropism landscape, as a reference, the cyan line is the ground level, and then that is the structural core to support the roof. And then we have the rain collection basin on top, which will collect rainwater and then put it into rain collection tanks below the ground. And then we have the soil for the trees. So the soil mound is shaped by the biomats. Biomat are biodegradable nets to control soil erosion. This is mostly from coconut. So the planting space is minimum 5 meter square per tree, which is the which should also be created as a structural scheme to support the trees. And then the tree and shrub species of endemic functionalistic tree assemblage would be growing on those architecture. And then these are the different variations of gravis stimulation on the landscapes. So we have 50 degrees, 60 degrees, 75 degrees, and 70 degrees. And you can see that every variation has a different height. We can see it in the section diagram that there are different heights in terms of the roof that is one of the manifestation of the gravity stimulation process. Okay, now for the plant list, these are the plant lists based on DNR, Dr. Madulid, and Dr. Lantikan. And then the phototrophism garden, the second type of growth biome in the site. The phototrophism is a process of differential growth by a plant in response to the direction of light. Through light stimulation, it can either be natural or artificial. Light stimulation is the process of stimulating plant growth by changing the source of light. So there's a picture on the right side of the slide of how it happens. The design concept is the same, with just the difference of plant growth simulation, which would now be phototrophism or the light parameter. And then the atmospheric morphogenesis would be the placement of skylight in relation to the vine gardens below it. So the design implementation, so that is the phototrophism garden in the bubble diagram. And this is the phototrophism biome in isometric diagram. And this is the ground floor plan, the second floor plan. This is the lounge, the record skipping area, the reading areas, and then on the second floor are the phototrophism garden. And then the structural system, the phototrophism simulation. And then these are the different configurations of the phototrophism garden. So you have four diagonal direction of the light source and a combination of the four to stimulate the plants into four diagonal direction. And then the second type is the perimeter growth. So it doesn't stimulate the plant to grow tall, but it grows perimeter, makes it fatter in terms of volume. And then the third type is the upwards growth of the direction of light source. So it stimulates the plant to grow directly up. And these are the plant list of the plants that will be planted on that facility, which are climbers. And this is the perspective of the facility. And you can see that the scientists are studying the plant growth that is going towards the light. And then the third type of growth biome is the soil and hydrotropism growth biome. So here, the main process is hydrotropism, which is the differential growth by a plant in response to the source, direction, and volume of water in the ground. The process of stimulating it is hydrostimulation, which is the stimulation of plant growth by the presence of water in the soil, where the plant is growing to create a differential growth. So this is the design concept is almost the same with the conceptual framework, with the difference of the soil and water parameter for plant growth simulation, and the atmospheric morphogenesis as the leveling and slope of the garden floors based on the cycle of water. So the non-controlled dependent variable is the plant growth, and the controlled independent variable is the architecture. Design implementation. This is the bubble diagram of the soil and water biome with its context of the theoretical framework. And this is the division in terms of the germplasm system phases. And this is the area of each space versus the site. And this is the floor plans. And this is the isometric diagram of the administration office. So this is the lower ground floor. So we have the reception desk, two librarian office, working areas, four is the meeting room, comfort room, six is the lounge, book collections, reading areas, veranda, and then this is now the ground floor itself. It's the lounge, the meeting rooms, the head office, the pantry, the comfort rooms, admin office, the logistics storage, which will connect the site 1 to site 2 in terms of storage of plants, and the security room, the records keeping area, and then on top of it is a cafeteria, a park, and the veranda where people can stay. So this is now the accumulation garden, the runoff garden, and this is the isometric diagram of the accumulation garden. So the accumulation garden or the number one or the gardens, it's surrounded by the landscape observatories where the scientists would be observing the plant growth. On top of it is the runoff garden, which also is also surrounded by the landscape observatories. And this is the form development. So you have the upper floor, which has high exposure to light and rain, and the lower floor, which has low exposure to light and an indirect exposure to water. And then I created a hole for the water access to lower floor, and then angled the first floor to create the runoff that it needs to connect the two floors. And then the water would accumulate on the lower floor. And then now we will plant the shrubs on the upper floor and mangrove below. This is the form development prototype number one. And then from prototype number one, I created a circulation that is more efficient. So the prototype two development. And there we connected the two floors. That's why it looks like that with the observatories as the major circulations for human use. So this is now the configuration of the runoff and accumulation garden cycle. So on top is the runoff garden, and then below is the accumulation garden. And then we have the shrubs on top and the mangrovetum below. We have on top is the fresh water from precipitation, and then below is the brackish water, which would be combined by the fresh water and the saline water that is coming from the tank to create the brackish water for the mangroves. And then the first process is precipitation. So you have water runoff. The architecture is designed for the water runoff to go down to the the floor below. And then this is now the precipitation with the runoff water. And then the water would accumulate on the lower floor in the accumulation gardens. And the roots would now have water absorption. From water absorption, we have evapotranspiration, which now will return the water into the atmosphere. And then it will rain again. And then the cycle goes on. And in terms of roots, the plant roots in runoff garden follow the direction of the water, and the plant roots in the accumulation garden seep the water for plant absorption. This is now the perspective of the soil and water biome, and these are the plant list for that biome. We have the shrubs and the mangroves, and this is the site development plan. From left to right, we have the Growth Biome Administrative Office, the Soil and Water Biome, the Egypt terminal that will connect the two sites, the Arboretum Walkway, the Arboretum Park, the Gravitropism Biome, the Phototrophism Biome, the Landscape Observatories, and the Arboretum of trees surrounding it. So this is now the perspective of the whole project for the party of the gravitropism growth biomes and light and soil and water. And this is the master development plan. So the two sites connected by the road, and then we have the natural zones surrounding it, which are the arboretum for endemic trees and the flower fields for the flowering plants. And these are now the research objectives and the design solutions. Research objective on the left and design solutions on the right. So the research objective is to provide the strategic location for plant conservation and germplasm conservation typology for modern conservation strategy. The design solution for that is the planning, site criteria, and placemaking through conservation-oriented restoration of the facility within the chosen site. Samar, the architectural thesis create a larger coverage of protected plants in Visayas and Mindanao region. The second research objective is to determine types of spaces and systems used for studying efficient plant growth. The design solution for that is through the provided hybrid biotechnology plant growth biomes. The thesis created new spaces that will answer conservation questions to provide more research on endemic plant in Visayas and Mindanao region. The third research objective is to apply existing protocols for plant growth and conservation studies. The design solution for that is the planning of the facility based on the three layers of types of spaces, which are based on the theoretical framework and the germplasm system phases. And the fourth research objective is to provide a collaborative social and scientific space. The design solution for that is a collaborative social space through medical and food garden that was located inside one's ecological corridors, which is the medicinal and the edible garden, which facilitates integration of Barangay Bagong Lipunan to the typology of the project. And with that, this is my thesis proposal, and thank you for listening.